today we're going to spend some time talking about the mean value theorem and also Rolle's theorem. I'm going to fly through this stuff a little bit, so pause, write things down, rewind if you need to hear me say it again, whatever it takes for you to get these notes filled out. So first of all is Rolle's theorem. There are a couple conditions for Rolle's theorem, the first one being f is continuous on the closed interval from a to b. So it has to be continuous. Second one, it has to be differentiable on the open interval, meaning no corners or kinks, jumps, those sort of things. And lastly, f of a equals f of b, which means it starts and ends at the same y value. So, for example, here's a, here's b, same y value, and regardless of how I connect those, somewhere there's going to be a slope of 0, like here or here or here. There can be multiple, there can be one, but there will always be one if it is continuous and differentiable and the endpoints have the same y value. So, for example, we could have this situation going on, and the slope everywhere is 0, which is at least one spot. B, we could have something going on where it goes up, and then we'd have this value C that had a slope of 0. Thirdly, we could have a situation where we've got A and B, and then we have this point C where the slope is 0. And if that's the case, where all of f of x is less than f of a and f of b, then f of c will be a local min. Not sure I filled that out on the previous page. F has a local max at c. By Fermat's theorem, f prime of c would be 0. Fermat's theorem or Rolle's theorem. Now, case D could be where f of x is greater than a, but also less than b, so something like this, which means we'd have a c1 and a c2, both of which have a slope of 0. F of c1 would be a local max, f of c2 would be a local min. Theorem 5. Mean value theorem, very similar, still continuous, still differentiable, but the beginning value and the ending value don't need to be the same. What it says, then there is a number c such that the slope at c is equal to the average rate of change of the whole graph. And I'll show you what I mean. Or we can multiply by b minus a. We get this situation. And the slope from a to b, theorem 3, this is simply how you find slope. So, for example, let's say that we have a graph like this, and we know, here's what the theorem says, f prime of c equals f of b minus f of a all over b minus a. The right side of that equation is the slope of that dashed line I just drew. What they're saying is the slope from the beginning point to the ending point is the same at some other point on the function. So, if you notice, there's probably a point down here that has that same slope. Probably a point up there with that same slope. And down here. My green lines are parallel to my red dashed line. And those are the locations that the instantaneous slope, which is represented by the green line, is equal to the average rate of change, which is the red dashed line, because slope between the endpoints is average rate of change, which we did early chapter 2. Now, next one says, verify that the function x cubed plus 4x squared minus 5 satisfies the hypothesis of the mean value theorem on the given interval from -4 to 1. This radical notation doesn't mean a whole lot to us until we estimate, and we get C to be approximately 0.119 and negative 0.2786. So, both of those values are between our negative 4 and our 1. And mine is just a sketch, but that would show us that the slopes are going to be the same over here somewhere, just past the x-axis at the 0.119, and somewhere around here, negative 2 point something. That looks a little bit to the left, but my graph is just a sketch, so it's not perfectly on. Theorem 5 is a bit of a common sense theorem. It says if f prime of x equals 0, so if the derivative is 0 for all x in the interval from a to b, then f has to be a constant. So if we have a 0 slope everywhere, the only thing it could look like is a horizontal line. So that's a bit of a common sense theorem. Now here's a corollary to Theorem 5.
Either is online.
If f prime of x equals g prime of x for all x in an interval from a to b, meaning the slopes are the same throughout the life of both functions, then f minus g is a constant on a to b. Meaning, if I take f minus g at any one x value, those red lines are all the same length. Same thing happens here. They're all the same, so that bottom function plus that value will get you the top function. So, again, a little bit more of a common sense function as well. Look these over, possibly check them out again yet today, come with questions tomorrow.